We're continuing our discussion of the spinning metal spherical shell. So for this shell with two conducting rods connected by a 10 ohm resistor on this metal spherical shell, first we calculated the tangential velocity of a point on the spherical shell making an angle theta with respect to the vertical axis. Then we calculated the cross product V cross B so that we can talk about the Lorentz force acting on positive charges. And in part C, we found the line element for the closest, shortest path between the upper rod and the angled rod. And that was our answer. Now in part D, what is the magnitude of the current in the wire? Okay, so as I said, because we know V cross B, QV cross B is the Lorentz force, we can therefore talk about the work done by the Lorentz force in this case. The work done, because this is an example of motional EMF, the work done by the Lorentz force is going to be equal to, for a charge dq, dw is equal to dq v cross b, the Lorentz force acting on it, dot product with the displacement, so it's the line element dl vector here, so dq v cross b dot dl. And if you look at dw divided by dq, the energy per charge, that is our EMF, voltage. So this is V cross B dot dl. So that's where the BVL formula comes from. This is our motional induced EMF. Okay, and how can I calculate this EMF? It is epsilon is equal to integral V cross B dot dl, and I'm going from theta is equal to 0 to theta is equal to 60 degrees to find the induced EMF. So that is from theta is equal to 0 to theta is equal to 60 degrees. Okay, so this epsilon is equal to integral from 0 degrees to 60 degrees. Our velocity vector minus 1.26 sine theta in j hat direction. That's the answer to part A. Dot product, that v cross b vector, that's the answer to part B. Dot product with displacement 0.1 cosine theta j hat minus sine theta k hat d theta. And we know that j hat dot k hat, they're perpendicular, is 0. So for this induced EMF here, we can write integral from 0 degrees to 60 degrees minus 0.126, because it's 0.1 times 1.26, sine theta j hat dot j hat is equal to 1. So it's sine theta cosine theta d theta. The other term, j hat dot k hat, gives me 0. Now, in order to perform this integral, let's say that u is equal to cosine theta, so that du can be written as minus sine theta d theta. And here I want to note also cosine 60 is sine 30, which is something I will need. That's 1/2. And cosine 0 is 1. Okay, so I will need it at the end. So this is going to be minus 0.126 integral u du from u minimum to u maximum, which I haven't determined. And that integral gives me minus 0.126 u squared over 2 evaluated between u minimum and u maximum. And I can substitute now for u cosine theta. So this is minus 0.126 cosine square theta divided by 2, which is to be evaluated between 0 and 60 degrees. Now you see I know what cosine 60 is and I know what cosine 0 is. Cosine 0 is 1, cosine 60 is 1/2. So this is minus 0.126 divided by 2, 1 over 2 squared, 1 over 4, minus 1 squared, minus 1. All right. So if I calculate this number, 1 over 4 minus 1, minus 3 over 4 multiplied with minus 0.126 over 2, I will find the induced EMF epsilon to be 0.0473 volts, and the current is this induced EMF epsilon divided by the resistance of the conducting path, which I assume only comes from this 10 ohms here. The rest has negligible resistance. So this gives me 4.73 10 to minus 2 volts divided by the resistance 10 ohms. So the current is finally 4.73 milliamperes. So what have I done here? I know V cross B from part B. I know dl vector from part C. V cross B dot dl is the induced EMF, d epsilon. But this is going to be done for angles between 0 and 60 degrees along this path. So for this path integral here. So I have performed this integral from 0 to 60 degrees to find the induced EMF, and the answer was 0.0473 volts. The current is induced EMF between these 2 points divided by this resistance, 4.73 milliamps. Part E, what direction does the current flow in the vertical rod? Okay. So since the Lorentz force points in which direction? So V cross B, Q V cross B, that's the direction of V cross B. Direction of V cross B is minus J hat. So I see that the Lorentz force points in minus J hat direction. The current loop, that's the direction of the Lorentz force. You can see here, minus J hat direction. The current loop that is formed by the sphere, the 2 rods, and the wire. So for this path here, positive charges should move from this side to this side. So I will see that there will be current flowing in this direction, in this direction, in this direction, and in this direction. So that's the direction of the current. So I notice that the 2 rods and the wire will allow positive charges to flow in the which sense? You can see this is clockwise sense. In the clockwise sense, which is equivalent to saying the current flows up the vertical bar. So that is up the vertical bar. Okay, so I have decided on the direction of the current by looking at the direction of the Lorentz force acting on positive charges. Positive charges are forced from here to this end, so therefore they will be following the shortest path here, which means current is flowing in this direction, so you can see it's clockwise sense up the vertical rod.